right here in the handout, we're talking about a systematic approach right here of evaluating the molecule for its chemistry and its physics or its properties. And you see where it starts with electronegativity and bond polarity, and then goes to some other topics, molecular electrostatic charge properties, called formal charge and partial charges, and resonance and molecular polarities, and finally molecular geometry. All these topics go into determining what the chemistry is for a molecule. Once you draw it out in a Lewis structure, then, well, what will it do? Well, that's what this is all about here. So we've already talked about electronegativity. And we know that it's from a standpoint of each element, it's an element's attraction for electron cloud. But how does the electronegativity affect the chemical bond? So when we expand electronegativity into the chemical bond, we're talking about bond polarity. And to connect these two ideas is very important in understanding how a bond makes or breaks. Now, consider, for example, the trend in electronegativity going across and down the periodic table. We have increasing electronegativity across the periodic table and decreasing electronegativity going down the periodic table. Now, the most important ones are carbon, nitrogen, oxygen, and your halogens. So when you're talking about trends in electronegativity, we're talking about increasing electronegativity for carbon. The nitrogen is more electronegative than oxygen, than carbon, and oxygen is more electronegative than nitrogen, and fluoride highly electronegative than oxygen. And then as you go down, you have a decreasing electronegativity going down, that because of the size. The size factor changes the influence of the nucleus on the valence level. So it's very important that you kind of keep this in your mind as we go through the remaining portions of the sections here. So I'm going to take carbon, and we're going to hook it up to carbon, and then we're going to hook it up to nitrogen, oxygen, and then, say, fluoride, like this. So what should you expect when this bond is formed? Well, carbon and carbon have the same electronegativity. So what this would generate is a nonpolar covalent bond. And the electron symmetry is called a symmetrical, nonpolar symmetrical distribution of charge, if you want a mouthful of it. Let's see. So it's a symmetrical. That means the distribution of charge is even all the way around it. There's no greater amount of charge around one of the carbons or the other. And because of equal electronegativity, neither one is influencing the other. However, when you get to nitrogen, you see nitrogen has a higher electronegativity in here. And so we're looking at the nitrogen pulling on your carbon. And see this little symbol right here. So we'll see with oxygen even greater effect, and an even greater effect with the fluoride. And as a result, the more electronegative element will remove some of the electron cloud from the carbon. And you'll see a distribution more like this. And then it'll even get even larger as we go down. And there's very little left over carbon in this. So these are now unequal or asymmetrical distributions. And are polar covalent bonds. And as they shift toward the more electronegative element in each of these cases, one way to think of it is we uncover some of the nucleus of the adjacent carbon in there and creating a dipole. That's why I drew the arrows as I'm showing you here. And on the carbon end, we make a little S with a little circle on the bottom of it and put a positive up there. That means that end of the molecule is a positive center, is what it's referred to. And this is negative. And the same way with the carbon-oxygen, carbon fluoride. And the more electronegative end is listed as a little partial negative and a partial negative like that. And those are common notations you'll see in molecules. Oxygen, hydrogen, you'll see people write these kind of notations between the bond structure showing that one side is more positive and the negative side is more electronegative in there. So now another thing that is happening in the asymmetrical distribution, it functions to weaken the bond. See, this is a high electron density here in the symmetrical. And then you get down to the carbon fluoride. This is a low electron, well, I'll move it up on the chart so you can see, low electron density. So when you get a high electron density, you translate that into a strong bond. But when you are bonding in with a highly electronegative element, that means it's a weaker bond. And that translates to easy to break. More reactive. So when you have these kind of structures in a molecule, you say, well, there's a real reactive center. And it will react with something else that's looking to positive looking for negatives is really what we're ultimately talking about. For example, I don't know if this chair is going to hold together or not. If we had something like carbon, let me draw it. This is a kind of a three-dimensional arrangement. All right, let's say we've got that molecule right there. And there's a very highly electronegative fluoride. Okay, so it's strongly dipolar toward that fluoride. And we have a weak bond. Okay, and it's partial negative, partial positive. Well, out here somewhere you have, say you threw in some sodium hydroxide, and that would provide this molecule, this polyion, your hydroxide polyion. Well, this center right here, this would be highly positive because of this dipole. And so this would have a tendency to be attracted to that center. And you would have for a moment bond that would do this. That's called a reactive intermediate. Right here, but it only lasts for a minuscule of second. And because this bond is coming in from a lower, let's put it that way, lower electronegative element, it would not distort the bond, and as a result forms a stronger bond. It would be a lot stronger bond than the carbon fluoride. And this one would be a very weak bond because of the electronegative distortion in here. And the results would be, you would make a different molecule. And the fluoride would disappear, and this is called a leaving group. Now, as a generalization, low electronegative fragments will always replace high electronegative fragments. So it doesn't matter whether you know what the molecule or fragment is. It's just if you have, say, a carbon with a strong formal charge right here, or a nitrogen, or an oxygen. A nitrogen wouldn't have the formal charge, or an oxygen. These have electronegativities. And if you were trying to attack something with a high electronegative group attached to this molecule, these would go in and break that bond. They would substitute. Why? Because these lower electronegativities form stronger bonds. And that's true for all chemical reactions. So as you look at the periodic chart, carbon, nitrogen, oxygen, and halogens, carbon will replace anything that's got nitrogen on the group, or if it's a charge, if it's neutral, it's not going to do anything. Nitrogen will replace oxygens. Oxygens will replace fluorides. Nitrogen replaces fluorides. Carbon. So it's all these are low electronegativities will replace the high electronegativities. So that's what we mean by molecular dynamics. So when you have a molecule, it looks like this. Let me just do it like this. And what would you add in there to react with it? Well, water will break down into this, and so that's a lower electronegative fragment. And we'll go in and kick the chloride out, and you would have this molecule that'll do this. It doesn't matter whether you know what I'm talking about here in terms of the molecule. Is that this, you see an oxygen replacing a halogen, because the oxygen is to the left of the halogens. And that's why we call the molecular dynamics, because that will replace anything in here. If you have something over here that's got a nitrogen on it, that'll replace all of it too. So that's what I'm saying, is looking at the periodic chart, seeing that electronegative trend, and saying, okay, something over here would have a low electronegativity. We'll replace anything over here with a high electronegativity. But high electronegativities are usually the ones that are called the leaving groups. on the other side of the molecule. So throwing this in, you would get T-butyl alcohol out of it, and you have some hydrochloric acid left over when everything's said and done. So when I talk about electronegativity and polarity, electronegativity is an issue that you need to understand in the chemistry of what the molecule is doing. The low electronegative fragment will attack a high electronegative fragment. Here's one that looks a little different. Take methanol. It looks like this in a geometric format. And then you have what we call acetyl chloride. I don't expect you to learn what this is in acetyl chloride. There. Now what do you see in terms of the structures? Well, I've got a molecule which contains an oxygen in it. And then I've got a molecule that contains a highly electronegative fragment over here. And so if I mix these together, this electron pair is going to go right there, because that is a very electronegative bond. It's going to leave that positive right there. And so when that happens, this thing goes to this. And you have acetic acid from the acetyl chloride. But it's not because you knew about you just simply knew that oxygen was less electronegative than the chloride and will replace that chloride, but it's got to attack the bond at some point. That's why I said carbon chloride bond highly, and so this is partial positive, and so that's where it's got to attack. It's all positive searching for negatives. And so that's what I'm talking about, molecular dynamics. It can be confusing, but simplify the rule is the lower electronegative will replace a higher electronegative. Okay. Electrostatic charges of substances, formal charge and partial charges. Yeah. Given a molecule, let's see. See, that's just a little group on there. And there you got that. What's the charge on this atom right there? When we talk about charge, on that, we call it a formal charge. And they're pretty easy to calculate. Formal charge is really the element in that structural bond that is in this arrangement like that. Well, it's valence minus bonded electrons divided by 2 minus non-bonded. So, in this particular issue, the formal charge of this structure nitrogen in that structure. The valence is 5 off the periodic chart. Now, when I say total number, now, a while ago we were just counting bond pairs and things. In this particular calculation, you have to take into account all of the electrons. Each bar represents an electron pair, so we're talking about 6 electrons. So that's 6 over 2. And it doesn't have any dots on it, okay? So it has 0 non-bonded pair. So when you make this calculation, the results of it is the formal charge on that element. So it's a 5 minus 3, which equals a plus 2. So this is carrying a plus 2 formal charge in that structure. You know what I'm saying? And it all revolves around this. Okay, let's see if I can give you some examples here. Okay, let's take the nitrite. Okay, if we draw the Lewis structure on this, we got 2 oxygens around a nitrogen. I'm out of chalkboard here. We'll come out with oxygen, nitrogen, oxygen. And this is your net charge. Now, what I want to calculate or show you here is the formal charge on each element in here, and then when you add up all the formal charges, you get this net charge in here. Hang on. Okay, back to where I was. So I want to calculate the formal charge on each one of these and then add up the charges. Now, it already conforms to the octet everywhere. You can see that. So I want the formal charge on the double bond oxygen right here. Then I want the formal charge on the double bond to nitrogen, single bond to the other side. And then I want the formal charge on the oxygen with 3 non-bonded pairs on it. See how I'm breaking down the molecule in this context? I'm just taking the bonds and the molecule along with its non-bonded pairs. Now, the valence is formal charge is valence minus bonded electrons over 2 minus the non-bonded associated with that element. So when we see the valence, let's take oxygen, is 6 valence, and the bonded electrons on there are 4. All you have is 4 electrons in here. So that's 4 over 2, and then you have minus the non-bonded, that's 4 also. So that's 6 minus 2 minus 4 and 0. So the formal charge here is 0. Now we want to get the nitrogen structure. The valence of the nitrogen is a 5. 1, 2, 3, 4, 5, 6. 6 over 2 minus 2. So you have 6 bonded electrons in there, all total. Now there's 3 bonded pairs, but 6 bonded electrons. Here's 1 non-bonded pair, but 2 non-bonded electrons. So that's 5 minus 3 minus 2. That's also a 0. Then we go to the oxygen with 3 non-bonded pairs, and 6 minus 2 over 2 minus 6, and that gives us a minus 1. So this one has a minus 1, and so that really accounts 0 plus 0 plus minus 1 gives you the net charge of a minus 1. So that's what I'm talking about when I talk about calculating the formal charge, because you're breaking down the molecule. See if we can do this one. Okay. Now, the Lewis structure for this is this. And you got a overall -2. Tell you what, I'm going to make it even more interesting. Take these out. Like that. So you have 4 sulfur-oxygen structures, and all we're interested in is each one going around, and then the sulfur in the middle here. So formal charge on the sulfur oxygens, because it doesn't have any support. So I'm just let me take the sulfur out. That confuses you. So valence is 6. We got 2 over 2 minus 3, 6. Sorry, and that's -1. So every one of these has a -1 charge. So you have 4 of them. Now I want the formal charge on sulfur. It's made up of this, and that's 6, and that's 8 over 2 minus, well, we have no bonded pairs, no non-bonded pairs, or no bonded electrons. And so that's 6 minus 4, which is a +2. So this would be a +2 charge in there, in that one. So when we add up all the formal charges, we have 4 times -1 plus 1 times +2, and so that gives me a -4 plus 2, or a -2, and that's your net charge. And so that's where all that comes from your ability to calculate each one of those formal charges, and then add them up, and you get the polyion charge. Of course, you learn the polyion with the charge, and that's sufficient for writing your molecules and stuff. But when it comes down to chemistry and reactivity, formal charge is a very important aspect of what's going on in your reactions. Okay.